Ellipses. Anyone know? No? Have you guys heard of elliptical orbits? How about the elliptical machines that you used to work out on? Okay. The motion of those are the way how those feet move on the bottom. Those are in the shape of an ellipse. Okay. All of our planets in our solar system follow an elliptical orbit. All right. So these are, I mean, they look like ovals. They're stretched out circles, but they're not ovals. They have different properties. So hopefully you have this chart already printed off when you printed off your parabola stuff. Hopefully you just printed the whole thing off and you've got this out. So an ellipse. The definition of an ellipse is a set of all points in a plane such that the sum of the distances from two fixed points, the foci, is constant. So what that means is here's a diagram of an ellipse down here. This would be our two foci points right there. Foci is plural for focus. So if you go to any point on your ellipse, the distance from each focus point to that point is the same. So if you add those two lengths together, it's the same. If you do a point way down here, add the two lengths together from each focus point, it is the exact same. So that length, the total between there, is constant.
So the focus thingy is always on the out?
No, the two foci points are these 2 points in the middle. Those are set and they never move. Okay? So it's got two foci points in the somewhere inside of it. They're set and they never move. So we have standard form for this, and we also have some other information about it. So standard form for an ellipse. Two standard forms, you're going to see that they look very similar. So here's the first one. X minus h squared over a squared plus y minus k squared over b squared is equal to 1. So what are some similarities to this standard form from our circle standard form? Okay, so we have the x minus h squared and we have the y minus k squared. What are the differences between this standard form and the circle? Yeah, so in a circle we had this equal to r squared, right? Here for an ellipse, we have two denominators, and these denominators are separate lengths. So this is an a squared and that's a b squared. That a squared and b squared is going to represent how far our ellipse goes in each of those directions. So x minus h squared over here is with the a squared. So that tells us in the x direction we're going to go a distance of a each way from our center. Y minus k squared is with our b. So that tells us in the y direction we're going to go a distance b away each way from our center. And for this, a is always greater than b for standard form. That's how we know whether to put our x first or our y first. Because if you look at our second standard form here, it's pretty much the same. The only difference is y minus k squared comes first, but it's still over a squared. Plus x minus h squared over b squared equals 1. So these really are essentially the same standard form. The only difference is which denominator is larger. That's going to be the value that comes first. Okay? So if you have 25 for a squared and if you have 9 for b squared, whatever the 25 is under, that's going to come first, whether it be your x or your y. And then whichever one is larger then determines if we have a horizontal or a vertical. Horizontal just means we're stretched more horizontally, so it's more elongated in the horizontal direction, and vertical means it's stretched more in the vertical direction. So for example, a horizontal ellipse would look more like that, a vertical ellipse would look more like that, but not quite that ugly. That's a really ugly one. Okay, so that's all the horizontal and vertical is saying. So essentially, is the x attached to the larger number or is the y attached to the larger number for the denominators? This, though, has the same center as a circle. So the center, notice the center for both of them are HK. That's the same idea for the circle. That was the same idea for the vertex for our parabola. And then we have foci points. The foci points, if we're in the horizontal direction, the foci points are going to go plus or minus in the horizontal direction. So with this H, so we'll have H plus or minus C, and then K. And if we're vertical, it's going to be plus or minus in our vertical direction. So we'll take our K plus or minus C, and our H will stay the same.
Do you add them and subtract?
Yeah, we add and subtract because there's two foci points. So from our center here, if this is our center, we would add A to get to that foci point and subtract A to get to that foci point. And I definitely just wrote in highlighter. That's okay. Major axis and minor axis both have the same. Major axis is 2A, and minor axis is 2B. So those are the same for both. Now the only thing up here that we don't have a set value for is what our C is. Okay? For our foci points, we just have this C value that happens. The way how we get C here is from this formula. C squared is equal to A squared minus B squared. Yeah, foci points are the two set points that are the same distance away from the center. So foci points for this example were right here and right here. They're the 2 points that are set in stone that are going to determine what your ellipse looks like. Okay? Right, the 2 foci points are on the longer axis of your ellipse. And the way how we find that distance is that C squared is equal to A squared minus B squared. Now this kind of looks like the Pythagorean theorem, right? But what's different about this?
It's not here, subtracting.
Yeah, we're subtracting. This actually is the Pythagorean theorem. However, A, B, and C conventionally, we use A and B to represent our two legs and C to represent our longest side. But for an ellipse, A is actually our longest side because that's the length of our major axis. So A ends up being the hypotenuse, and B and C end up being the two legs. So it is the Pythagorean theorem. It's just not conventionally with the letters that we use. So it's C squared equals A squared minus B squared. Good way to remember this is you do opposite of its addition here for the ellipse, so you do the opposite sign to find C. That'll make a little bit more sense when we do hyperbolas because that's got a similar relationship. So to sum up this ellipses, so ellipses, they have two axes of symmetry. They have the major and the minor. The major axis has the foci points. So whichever way it's elongated, that's going to be the axis that has those 2 points that are set in stone that are never going to change. The minor is just the other one. And then the center of the ellipse is where that major and minor intersect. Okay? So on this diagram over here, this would be our... Are you not working? That would be our minor axis, okay, because it does not contain the foci points. This would be the major because it does contain the foci points. And the center is where those two axes end up intersecting. The center would also be the midpoint between your two foci. Just a few other pieces of information about this diagram. I'm going to clear it off so that we can draw on it a little bit more. A couple other things. So here's the center. The distance from the center to the edge on the major axis, that distance is B. And it has that same distance on the other side. That distance is also B. That's why when we say the length of the minor is 2 times B, because the whole way across would be 2B. Similarly, from the center To the top of this ellipse would be a distance of A. And then from the center to the bottom would be another distance of A. So that's why the length of the major would be set as 2A. All right, so we're going to try some examples with this. So we want to write an equation for this graph. Okay? So in order to write the equation for an ellipse, we need to know what our center is, and then we need to know what our A value is and what our B value is. So here for this graph, I know 4 points, and we only know the points that are actually specifically given. It may look like it's hitting another point, but we don't know that exactly. So here this top point is at 2, 7. The bottom point is at 2, -5. And then we're given the 2 foci points. This one is at 2, -2, and that one is at 2, 4. So first off, let's try to find where the center is. So where would the center of this be? Yeah, just halfway in between here. So if we're at 2, -2 and 2, 4, here would be our center at 2, 1. So the center is at 2, 1, which means that that is our H and our K value. Now we need to figure out what A is and what B is. A, we can find because it's the distance from the center to the edge of the ellipse on the major axis. So this would be our major axis because it includes our 2 foci points here. So what would be the distance from the center to the edge of the ellipse?
6.
Yeah, 6. So that distance right there is 6. So since that distance is 6, that means A equals 6. Now we need to find B. B would be the distance from the center to the edge on the minor axis. But we were not given that point exactly. All right, so we're going to have to look at another way to find it. What other points were we given exactly? Yeah, the foci points. So here, what's the distance from the center to the foci point? 3. That distance from the center to the foci point represents C. Okay, so C here would equal what? 3. And then we can use our C squared equals A squared minus B squared to figure out what our B should be. Nope, that's a coincidence that C is half of A. C is the distance to the foci point. And it's going to be different for every ellipse.
C is foci to A.
Yeah, C is center to the foci. So we have our C, we have our A. And for ellipses, C squared is equal to A squared minus B squared. So we can use our C and our A value now to figure out what B should be. So our C is 3, so we'd say 3 squared equals, our A is 6, so 6 squared minus B squared. And we just have to solve this for B. So how could we do that?
Square and then subtract.
Okay, so square. So this would be 9 equals 36 minus B squared. Then what? Okay, we can minus the 36. So what's 9 minus 36? Yep, negative 27 is equal to a negative B squared. Yeah, square root it, but before we square root it, what should we do with the 2 negatives? Yeah, divide it by -1 so it makes them both positive. So then our B squared is 27. According to our formula, we only need to know what B squared is. Okay, we don't need to know what B is, because in our standard form, we just have B squared. Okay, so now we're going to write this in standard. So we need to decide which way are we more elongated, in the y direction or in the x? This was negative B squared equals negative 27, so if we divide both sides by a -1. Yep, so we're elongated more in which way, the y or the x? The y. So since we're elongated more in the y, we're going to start with our y value. So y minus, oopsies. So y minus k. So what's our k value here? Yep, so y minus 1 squared over a squared. So 6 squared is 36 plus x minus, what's our h? 2. So 2 squared over, we got our b squared to be 27, and that's equal to 1. So there's our standard form. No, this would be the equation. We just wanted to find the standard form for this. The way how we would solve it would be to graph it, and we already have the graph for it. Mm-hmm.
So how do you figure out if you want to do y first again?
Okay, so we figured out that y wanted to go first because if you look at our ellipse, it's elongated more in the y direction, or our foci points here were moving up and down from our center. So that meant that our y had to come first.
Since it was 2-1 on the graph, in the form is minus, you have to change it?
Correct. Our form is minus, so we have to make sure that we do y minus 1 instead of y plus 1. Correct. Yes, Joshua? Yes, if this were longer in the x direction, the 36 would still be first. The larger number in the denominator should always be the first one there. Okay, so let's try graphing one. So here's our equation. We want to graph it, state the center, the foci points, how long our major and minor axes are, and then graph it. So we'll start with one that's already in standard form. So x squared over 36 plus y squared over 9 is equal to 1. So where would our center of this ellipse be?
0, 0.
Yep, at 0, 0. So center is at 0, 0. Okay, there's nothing being added or subtracted to either our x or our y. So our major axis is 2a. So if a squared here is 36, what would a have to be? 6. So what would be 2a? Yep, 12. So our major axis would be 12. Our minor axis is 2b. So here b squared is 9. So what would b be? 3. So 2b would be 6. From our standard form, a squared comes first and b squared is second. Our major is 2a and our minor is 2b. Yep, so we would multiply our a or our b value by 2. And then our foci points here, we're going to need to figure out what c is. So c squared is equal to a squared minus b squared. Now, the beauty of this formula is that we already have a squared and b squared. We don't have to square anything. Our a squared is sitting right here. It's the 36, and our b squared is the 9. So we can go, okay, c squared should be 36 minus 9. Well, it's 36 minus 9. Yeah, so c squared is 27. To get our foci points, we need to go the actual c value, though. So we want to do the square root of it to get the c value. And we're going to leave that exact. So the square root of 27, how does that break down exactly? Yeah, 3 square root of 3. So no decimals there. Do the exact, do the breaking down of your radicals. So now the foci points, here we have to decide, are we stretching more in the x direction or stretching more in the y direction?
How do you know that?
By the variable that comes first. So the x direction, we're stretching more. The x came first, and it has the larger denominator. So since we're stretching more in the x direction, the c value gets added and subtracted to our x center here. So our x center is 0. So we don't need to write 0 plus or minus. We can just do plus or minus 3 root 3 and then 0. So we'll graph it now. So start with your center. Okay? And then if you look at your equation, what value is attached to the x squared? So what value is in the denominator of the x squared? Yep, the 36 here. So x squared, the 36 is in the denominator. So we just want to figure out the square root of 36, which is 6. So in the x direction, we're going to go 6 each way and put a point. Then we do the same idea for then the y. So y squared is attached to 9. So what's the square root of 9? 3. So we'll go 3 each way in the y direction and plot those 2 points. And then I'm not going to make you put string on your paper and figure it out. So we're just going to take those and we're going to do our best job that we can to connect them. So that would be our graphed ellipse. And then we're just going to put the 2 points in there for the foci points about where they would be. So we saw that the foci points for c squared, we got 27. So what's a square root of 27? What's that about? It's a little bit bigger than what number? 5. A little bit bigger than 5. So from the center, we'll go a little bit more than 5 away. There's one of our foci points. Go a little bit more than 5 away the other direction. There's our other foci point. We're not going to leave it as a decimal for our exact solution because that's not precise. On your graph, though, you can't precisely graph 3 root 3. Mm-hmm.
So then why would you use the 3 root 3 when you could just do the 27 square root?
You can do that on your graph. However, for your final answers, you need to have exact solutions, not a decimal. Is that one okay? All right, we're going to do another one. And this time we have to put it into the form. So x squared plus 4y squared minus 6x minus 16y minus 11 is equal to 0. We're actually going to put this in standard form a lot like how we put circles in standard form. And we're going to kind of combine the idea of circles in standard form with parabolas in standard form. Okay? So for circles, what did we do with our x squareds and our x's and our y squareds and our y's? Yeah, we got them together. So that's what we're going to do first here. So we're going to put our x squared minus our 6x together in parentheses. We're going to put our 4y squared minus our 16y together in parentheses. And then what did we do with any numbers that we had? Yeah, we added them to the other side, so we're going to do the same thing here. And now we want to complete the square, but I see a problem with my y's. I can't complete the square yet with the y's. Why not? Because we have a 4. So we have to take care of that. So the x squared minus 6x stays the same. What can I do with that 4? Take it out. So I'm going to take the 4 out, and I'll be left with y squared minus, 4y.
Wait, how come that goes to 4 because you divide?
Yeah, because we divide this 16 by 4 because we took it out.
Aren't these like square on the top, so they have like the little two?
Yeah, we have to complete the square in order to get them to be squared. So now we'll complete the square for both of these. So when I complete the square for my x squared minus 6x, what do we add here? 9. So what should I add to the other side? 9. Y squared minus 4y, what should we add? 4. Now on the other side, I should add 4, but also do what with it? Yeah, also multiply it by 4, so it's like adding 16. So now we'll write what we have. We have x minus 3 squared plus 4 times y minus 2 squared is equal to 36. How did we get what? We got the 3 because this is x squared minus 6x plus 9. It would factor to x minus 3 times x minus 3, or x minus 3 squared. Now, in the standard form, what is the equation equal to? It's equal to 1. So how can I make the 36 into a 1? Well, sure, we could subtract 35, but this doesn't have a subtraction over here. Yep, so we can divide by 36, and we'll make sure we do that everywhere. Okay, so this then tells us we have x minus 3 squared over 36 plus, what would 4 over 36 become? Y minus 2 squared over, 9 is equal to 1. So there's our standard form. So it's combining the two ideas of completing the square together for what we were doing. And is our denominator that's larger, is that the one that's coming first?
Wait, how come you got a 9?
4 over 36. 36 goes into 4 9 times, so that would be a 9. And for our denominators, is the larger denominator coming first? Yep, so we know we have it set up the right way. So what would be our center here? It would be positive 3, positive 2. What would be the length of our major axis? So this is our a squared is 36. Our major axis is 2a. So it would be 12. Yeah, because the square root of 36 is 6. 6 times 2 is 12. What would be the length of our minor axis? 6. And then to find our foci points, we would have to do c squared equals a squared minus b squared. Well, this looks familiar. I think we just did this one last time, right? 36 minus 9. So c squared is 27, or 3 root 3. What would I have to add and subtract that onto? My x value or my y value? My x value, so my foci points would be at 3 plus or minus 3 root 3, and then 2. So now we'll graph all this. So we'll start at the center. So we'll go to 3, 2, and I see that I'm going to go off the graph. So I'm just going to move this over. So there's my new y-axis. So I'm going to go to 3, 2 for my center. How far out in each direction will I go in the x? Yep, I'm going to go 6 out each way. How do we get 6? Yep, it's the square root of our 36, so we'll go out 6 each way in the x direction. How far out each way do I go in the y direction? 3. Yep, how do we get 3? Yep, it's the square root of 9. So then you take those points and you draw your best possible ellipse you can. And then where about would I label my two foci points? Yep, a little bit more than 5 away. So there would be one of them, and there would be the other one. Okay, we'll start tomorrow off by doing one more example together, okay, which is similar to this one, but we'll stop there for today.